Swayam Prabha. Digital India. Educated India.
So, we would do today graph mean cut, and in that kind of see applications of this. Now, the algorithm that we would talk of for graph mean cut, I define this problem for you shortly, but this was like a very, this is a very, what should I say, very important as well as a classical problem in graph algorithms. And there were algorithms, the one I would discuss today was by someone called Kargar, coming up in the 1990s, and you would understand that it's like such an elegant and beautiful algorithm that it to have come so late in the day in computer science should have come much earlier. Now, so Venkatesh, I think, had done some randomized algorithms for you, but they were on numbers, arrays. This is kind of your first foray into something which is like kind of just beyond numbers. You would get into graphs. So, I assume that everyone knows what's a graph, right? You have a set of vertices and a set of edges which is nothing but a subset of V cross V. So, it is a relation, right. Okay. The graphs can be directed graphs, undirected graphs, connected graphs, simple graphs. So, in here we would be considering simple, undirected and connected graph, right. The simplest version of of a graph that you can think of. So, what is a simple graph? That for any two vertices you allow only one edge. So, you do not allow multiple edges, as well as you do not allow any self loops, because I said edge is a subset of V cross V, right. So, this XX can also be an edge, it is kind of a self loop on a vertex. So, I disallow self loops, I disallow parallel edges as well. Fine. So, what is the minimum cut for G? What you want to do is as follows, and this is a problem useful in clustering, in partitioning, in many places. I mean, the reason it is very useful is like many real life applications you can abstract as graphs, and then you want to divide it by tearing off the minimum number of edges. Okay. So, here is the definition for minimum cut. What I want to do is I want to pluck out some edges from the graph such that the set of vertex V breaks up into two disjoint components V1 and V2. Is the minimum number of edges So, mind you, this is a partition. So, partition means there is, if you look at V breaking up into V1 and V2, then V1 intersection V2 is null set. So, I require the vertex set V to be broken into at least 2, right. So, think of this as 2 vertex sets. So, minimum number of edges I need to pick out from the graph such that the graph breaks into 2 parts. So, is the problem clear? Fine. So, let us look at an example. So here is a 5 vertex graph. So what is its mean cut? 2. Which way would you cut? So you would cut possibly the edge, right. So this is your mean cut. So 5 on one side, and by removal of the edges 3, 5 and 4, 5, the vertices 1, 2, 3, 4 on the other side. So this is a cut. Fine. Now for a general graph G, what would you do to find the minimum cut? How would you proceed? What is your number of possibilities? Huh? Hold on. Do you call that an algorithm, right? An algorithm is like exponential. There are exponential algorithms for some certain problems, but for a problem as simple as this, would you want to spend exponential amount of time? Right? What you said was, I can have at most NC 2 edges in this graph. It is a simple graph, and so I either keep or delete each edge, 2 possibilities. So you are looking at 2 to the power of n choose 2 possibilities. Yeah.
N minus 1 edges, because at most one element can be connected to n minus 1 edge, and one vertex would be connected to n minus 1 vertex. But edges.
Yeah. So what I mean, what is your? I mean, I want an algorithm.
At a max, it can be connected to only n minus 1 other edges.
So
For a perfect figure, perfect graph, n minus 1 would be the answer.
no. Look into this. Hold on, come. So I have a graph, right? Not all graphs are completely connected, right? So I want a set of edges whose removal makes the graph into 2 parts. So how come I have a predetermined answer like n minus 1? There can be graphs for which only one edge is the answer, right? So give me and try to think of an algorithm of a sequence of steps which would lead you to find the minimum cut. Hold on, yeah. Start with the smallest degree vertex, okay? That's a good idea. Oh, right, this example is actually that. You did the smallest vertex, right? Smallest degree vertex. Let's see. Think of this graph, which is kind of a So I am looking at a particular kind of graph which is as follows. So that means for any 2 vertices, so so the graph looks like this. So it's n by 2 vertices on one side, n by 2 vertices on the other side. This n by 2 connected fully among themselves, right? And this n by 2 fully connected among themselves. And for 2 designated vertices, there is an edge. So this is now a complete simple connected graph on n vertices. Agreed? What is the size of the minimum cut?
1.
But if I go by minimum degree, which vertex would I pick? Somewhere inside it, right? So minimum degree is like kind of tempts you to get into minimum degree, but it's not going to give you the answer. Yeah, some more ideas. So minimum degree is like I would appreciate your idea in the sense that minimum cut should have something to do with the degree value. Think of this. Say for example, minimum cut is of size k, right? Then if you had in this graph a vertex whose degree is less than k, then you cannot have, right? Because if you did have, then you would have taken that vertex on one side of the partition, the rest on the other, and the number of edges from this vertex to that side is less than k. Cannot be, right? Because your minimum cut is of size k. So minimum cut has something to do with degree. We will explore that. But again, let us have some more ideas before that. Yeah, so this minimum degree idea is not going to work algorithmically. It might help me in proving certain bounds, but that we will see later on. So, a takeaway from your suggestion is that the degree of each vertex in this graph should be greater than or equal to k, where k is the size of the minimum cut, right. So, this is a takeaway. Fine. So, let us do this. Maybe we can take this as a lemma. This is our takeaway. For all vertices in this graph, degree V is greater than k, where k is the size of the minimum cut. So, proof I have already given, you do it as an exercise. So, you just argue that if it is otherwise, then the minimum cut has to be greater than k. Okay, so come up with ideas for the algorithm. We had one characterization. You know by now randomization. Can you get me some ideas from there? Okay, then so her idea is as follows. I have this graph, and for this graph there exists, mind you, there is no guarantee that your minimum cut set, the set of edges, would be unique, right. There can be many such minimum cuts in the graph. How many we will see later. Now say for example, you have this number of edges is E, of them you know K is the minimum cut size, right. So say there exists a cut C, Before I get into it, randomized algorithms are of two types. One is known as this Las Vegas randomized algorithms. The other is Monte Carlo. So, the ones Venkatesh discussed in the last day where there is no error are known as Las Vegas, and the one where there might be errors, where obviously I would put a probability bound on the error, would be this Monte Carlo algorithms. So, now what I am going to do is I am going to learn the first kind of Monte Carlo algorithm. So, I am allowed to err, right? I am allowed to make errors, but again we would prove a bound on the probability of that error. Fine, okay. So, the algorithm is as simple as this. What you do is pick an edge at random, uniformly at random, pick an edge. Then what you do is, so this is an edge between two vertices you have picked uniformly at random from the graph. Collapse these two vertices into a super node kind of thing. So, you started with an n vertex graph, you picked an edge uniformly at random, collapse these two vertices at the end of this edge into one vertex, right. Now, this new graph has n minus 1 vertices. You need to form these edges in this new graph in the following way. This edge which was between these two vertices gets deleted from this graph, right. What I have to now do is, what about edges that were going out from these two vertices? What I will do is, in the new graph, all other vertices remain except these two. These two vertices has been replaced by a kind of a super node. From this super node, I put edges to those vertices to which it earlier two vertices had edges to. Done? I again repeat the process in the new graph. Again pick two vertices. Now, of the two vertices of an edge picked uniformly at random from this new graph, maybe one vertex is a super node, right. But again you do the same thing. Collapse, we will see, collapse, again reassign edges, keep doing. So, at each stage you are reducing vertices by 1. Stop at the moment you have only 2 super nodes, right. You started from n, stopped when you had 2 super nodes. So, how many iterations did we do? N minus 2. Started from n vertices, stopped when we had 2 super nodes, n minus 2 iterations. Done. Now, what I do is, now see, corresponding to these two super nodes, there are vertices inside this, vertices inside this, that I declare as my partition. All edges going across are the cut. Is the algorithm clear? Okay. Let us do a small example with this for this algorithm. With that, I would do 2, 1. It's like you understand why I do 2. So contract the edge 3, 4. So if you contract the edge 3, 4, you have a super node corresponding to 3, 4. You have 1, 2 as earlier. This edge is undisturbed. Now from 3 there was an edge to 1. So from this super node there should be an edge. There was also an edge from 4 to 1. Right, I said when you collapse, whatever edges that are going out from these two ends should be retained. So 3 had edge to 1, I keep it from 3, 4 from this super node. 4 had an edge to 1, I also keep that edge. No longer this edge is a simple graph. This gets to a multi-graph because I start having parallel edges. Similarly, you have these two edges. Done? So I have got rid of one vertex. Now I have come down to 4 vertices, of which one is a supernode. Next, what you do is contract 1 and 3, 4. What do you get is a supernode of 1, 3, 4 and you have 2 and 5. Then contract 2 and 1, 3, 4. Yeah. What? I didn't get. No, as I said, pick an edge uniformly at random. Hmm. No, there can be many choices, as I said. I am just looking at one particular choice.
So if we randomly pick and club them, so at the end, whatever we get the degree sequence will.
What degree sequence? Let's just go with this example. Let's just go with this example. You will start appreciating things. Yeah.
Is it compulsory to take the?
There is nothing compulsory. I said
We can take any.
there are a bunch of edges in there. No edge is lost. You at any point of time pick an edge uniformly at random. Right? Whatever it is, I have given you the rule. So I said I would stop when I have 2 supernodes. So I stop here and I declare this as my cut, right. Mind you, for each edge selected uniformly at random, when I collapsed, that edge is lost, right. So just if you count the number of edges, you would understand which edges are lost. But what I needed was the partition of the graph into 2 subsets of vertices, disjoint subset. Now if you go back, this was what it was, fine. Now what you do is, okay, so what was my algorithm? I picked edges uniformly at random. So for example, in this case, this was picked first, then so I contracted 3 4, then 1 3 4 was like, this was picked uniformly at random, you got this one, and then 2 1 3 4, this was picked uniformly at random, right. So when you collapse, as I said, all edges between these 2 vertices go away. Now that means if during this sequence of collapsing edges I never touch an edge that belongs to the minimum cut set, then I am done. But while doing this collapsing, if I ever touch one of those edges in the min cut, then I will make errors. Now what you do is, to get yourself convinced, you look at this sequence of contractions. So in here, what you do is, first you contract 3 4, then you contract 3 4 5, next you contract 2 3 4 5. Do this yourself quickly. On the same graph. So start with this one, first 3 4, so you land up here, right. So you land up there, then instead of contracting 1 3 4, you contract 3 4 5. You contract 3 4 5 and then see what you get. You will get something like this if you are correct. Now see, what you did was, the moment you contracted this 3 4 5, you had touched one of those edges, and that is why this is a unsuccessful case. So by now you understand that there are sequence of contractions which might lead you to the minimum cut, and there are sequence of contractions which might take you away from the minimum cut. Done? So what, let's sum up this observation that we had. So if you have not touched any one of these min cut edges in any one of these n minus 2 iterations, you are done. Agreed? Okay. But this is now a probabilistic event, right? You may touch with certain probability, you may not touch with certain probability, because you are picking up edges uniformly at random. So somewhere down the line I need to figure out that what is the probability that, now think of modeling this as a random process. I picked up in my first iteration, I picked up an edge uniformly at random. I was happy if this edge did not belong to the min cut. So I need this probability. Probability that an edge picked uniformly at random in the first pass did not belong to the min cut. Right? Come to the second iteration. In the second iteration, I will be happy if I had not disturbed a min cut edge in the first iteration and not even in the second. So this is a conditional probability. So in the second pass, I need something like probability that no edge of the min cut was disturbed in the second pass, given that no edge was disturbed in the first pass. Come to the third iteration. No edge of the min cut disturbed here, conditioned on the fact that no edge was disturbed in the first and the second. So intersection of that. Are you now getting something like this? So I would now define my event as, say, an event EI as an event that no min cut edge was contracted in the iteration I. I runs from 1 to n minus 2. So if I can now figure out these individual conditional probabilities, then I am done with the error, right? Okay. So this is the, now we will get into the formalisms. Any queries till now? No queries for me is always a dreaded, a very dreaded thing, huh? Okay. Let me now define my events before I, make the effort to find them out. this n, computing 3-way intersection is difficult. So, it is like computing n minus 2-way intersection would be more difficult, and so that is why people take recourse to this chain rule. So, now I know that this is equals to done. This is what I have to now figure out. So, finding this out exactly might be difficult. So, what I would be possibly happy with is a bound on this, that this is greater than equal to something, and its complement event is the other side, that you fail with a probability at most this. So, this is kind of the success probability. So, success probability, I want it to be above certain thing. I want to give you a guarantee that it is always going to be something above something. For the failure probability, I would give you an upper bound on the failure probability. So, here I would want kind of a lower bound. So, that means I would want for each one of them a lower bound. Then I can kind of multiply them to get the final lower bound. So, let us now try to figure out this lower bounds. If we can, we are done. Okay. In here, this will help us a lot. Now, think of the first probability of think of the probability of E1. That is a very easy probability to figure out. Why? Because still the graph is kind of pure, no collapsing, nothing.